Hello, everybody, and welcome to this presentation of the paper titled Automated Generation of Markov Decision Processes Using Logic Programming and Large Language Models for Robotic Applications, submitted for review at ICRA. Here is a motivational example to showcase why this work is important. In this scenario, we consider a worker here in the building area that has to build the structure in a certain way. The robot is providing the blocks that the user can use in order to build the building, and it is providing them by picking them up from this block tray where it can pick whatever block it wants. Now, the goal is for the user to complete the structure with as much freedom of choice as possible. So the blocks here in the pickup area should be as varied as possible. And also, we want to follow a certain policy when building something, building a structure, so that the user does not make mistakes. Now, this policy can be evident or can be hidden from the user, and it is represented by how the blocks are positioned in the pickup area. So the closer the block it is to the user, the higher the probability that the block is picked up. Now, this, as I said, is a motivational example, but it's not on its own. It represents a more broader set of possibilities. And all of these possibilities can be modeled through MDPs. Now, the biggest problem with MDPs is the fact that they are quite hard to write down. And so the idea is to employ a series of actions that starts from a natural language description of the task and of the environment and allows us to extract the whole MDP, so the whole graph representing the MDP. And for doing this, we came up with this framework that works specifically on three main steps. The ability to generate a Prolog knowledge base starting from a natural language description using a large language model. Then it employs reachability analysis starting from the initial state, and it extracts the whole MDP as a graph, and it writes it inside a Prism file. And then we use a state-of-the-art model checker such as Storm to obtain the optimal policy for that MDP. Going a little bit into deeper, we see that we use few-shot prompting, which is a common technique for large language models, in order to tell the large language model how to structure the knowledge base. Doing so allows us to reduce the amount of code and text that we have to write every time that we want to create a new MDP, to simply writing down what actually we want and how our environment is constructed. We then move to the MDP generation part, where we start from the knowledge base that we created in previous step. We start from the initial state that is within there written down, and by testing all the combination of states and actions, we do the complete reachability analysis on the graph, and so we obtain an MDP that can be then written inside the Prism file. Here on the right, you can see a Prism file that is derived from a similar query passed to GPT-4. And finally, once we have our Prism file, we indeed can employ a model checker, a standard model checker such as Storm, to obtain the state action table, which can then be directly used for execution. And now I'll leave you to the complete experiment that we carried out in real life, showcasing the abilities of this framework.
Here we can see the robot picking up the blocks and placing them in the pickup area for the worker. We can see that for the first layer it presents only large blocks, which are the ones that must be placed as the base. Whereas here in the second action it will place two blocks of type base to incentivize the user on choosing them, but also one of type medium, which can be placed on top of the first base. The robot continues to provide different blocks so that the user can choose and continue to create the structure that it has to create.